Well, welcome back to our course on discrete mathematics as we look at some interesting things about discrete structures. We've been making some good progress as we go through all of the detailed content in Rosen. And what we're going to be talking about today is chapter 8, when we're going to be talking about advanced, excuse me, counting techniques. And we had a chance to begin to think about counting already. But in this chapter, we're going to go into more depth. So as we look at advanced counting techniques, these are going to be the things that we're going to refer to. The applications of recurrence relations, solving linear recurrence relationships, divide and conquer algorithms and recurrence relations, generating functions, inclusion and exclusion, and finally the application of inclusion and exclusion. So many counting problems cannot be solved easily using the methods discussed in chapter 6 when we were just talking about some regular, maybe more fundamental ways of thinking about counting techniques. One such problem is how many strings of length n do not contain two consecutive zeros. To solve this problem, let A of n be the number of such strings of length n, and an argument can be given that shows that the sequence of A and n satisfies the recurrence relation an plus 1 equals an plus an minus 1. And the initial conditions of A1 is equal to 2 and A2 is equal to 3. This recurrence relation and the initial conditions determine the sequence A of n. Moreover, an explicit formula can be found for a sub n, from the equation relating the terms of the sequence. As we will see, a similar technique can be used to solve many different types of counting problems. So we'll discuss two ways that recurrence relations play important roles in the study of algorithms. First, we'll introduce an important algorithm paradigm known as dynamic programming. Algorithms that follow this paradigm break down a problem into overlapping subproblems. The solution to the problem is then found from the solution to the subproblems through the use of a recurrence relationship. And second, we will study another important algorithmic paradigm, divide and conquer. And it can be used to solve a problem by recursively breaking it into a fixed number of non-overlapping subproblems until these problems can be solved directly. The complexity of such algorithms can be analyzed using a special type of recurrence relationship. And in this chapter, we will discuss a variety of divide and conquer algorithms and analyze their complexity using recurrence relations. We also see that many counting problems can be solved using formal power series called generating functions, where the coefficient of power of x represents terms of the sequence we are interested in. Besides solving counting problems, we will also be able to use generating functions to solve recurrence relationships and to prove combinatorial identities. Many other kinds of counting problems cannot be solved using the techniques discussed in chapter 6, such as how many ways are there to assign 7 jobs to 3 employees so that each employee is assigned at least one job, or how many primes are there less than say 1,000. Those are examples of the kind of things we can look at. Both of these problems can be solved by counting the number of the elements in the union of sets. We will develop a technique called the principle of inclusion and exclusion that counts the number of elements in a union of sets, and we will show how this principle can be used to solve counting problems. So a lot of interesting information, and as always the case, I'll be trying to keep it at a higher level from a survey point of view to be having us get a chance to be thinking about this. Okay, let's talk about the applications of recurrence relations So we can recall from chapter 2 that a recursive definition of a sequence specifies one or more initial terms and a rule for determining subsequent terms from those that precede them. Also recall that a rule of the latter sort, whether or not it's part of a recursive definition, is called a recurrence relation, and that a sequence is called the solution of a recurrence relation if its terms satisfy the recurrence relation. So in this section, we will show that such relations can be used to study and to solve counting problems. For example, suppose that the number of bacteria in a colony doubles every hour. If the colony begins with 5 bacteria, how many will be present in n hours? To solve this problem, let an be the number of bacteria at the end of n hours. Because the number of bacteria doubles every hour, the relation an equals to an minus 1 holds whenever an is equal to 2, an minus 1 holds whenever n is a positive integer. This recurrence relation together with initial conditions a0 equals 5 uniquely determines an for a non-negative integer n. We can find a formula for an an using the iterative approach followed by in chapter 2. Namely, an is equal to 5 times 2n for non-negative integers n. Some of the counting problems that cannot be solved using the techniques discussed in chapter 6 can be solved by finding recurrence relationships involving the terms of a sequence, as we have done in the problem involving bacteria, which we just discussed. So in this section, we will study a variety of counting problems that can be modeled using recurrence relations. In chapter 2, we develop methods for solving certain recurrence relationships. And in section A2, which we'll get to shortly, we will study methods for finding explicit formula for the terms of sequences that satisfy certain types of recurrence relations. We will conclude the section by the introduction of algorithmic paradigm of dynamic programming. After explaining how this paradigm works, we will illustrate its use with an example. So there are a little bit of some of this information that goes beyond what we have in these charts. And so I'd refer you to Rosen to getting a full set exploration of that. Okay, in terms of recurrence relations, here we have a definition. A recurrence relation for the sequence a sub n is an equation that expresses a sub n in terms of one or more of the previous terms of the sequence, namely a0, a1, all the way up to a sub n minus 1, and for all integers with n greater than or equal to n0, where n0 is a non-negative integer. So a sequence is called a solution of a recurrence relation if the terms satisfy the recurrence relation. The initial conditions for a sequence specify the terms that precede the first terms where the recurrence relation takes effect. So here's an example, and we'll have a couple of slides that go over this. So a young pair of rabbits, one of each gender, is placed on an island. A pair of rabbits does not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produces another pair each month. Find the recurrence relationship for the number of pairs of rabbits on the island after n months, assuming that the rabbits never die. And just give some context, this is the original problem considered when we explored the Fibonacci sequence, which we'll get into again as we continue to go through this chapter. And this was back in the 13th century. So this just gives us an idea of what it would look like as we can be looking over months. How many pairs do we have? What are the young pairs? And so thus we are able to model population growth of rabbits on an island or any other kind of growth function that we would want to consider. And so this is where we can see this relationship to the Fibonacci numbers. Okay, here is the solution. I won't go through this in detail, but you can pause the video and see this, but let f sub n be the number of pairs of rabbits after n months. There are f sub 1 equals one pair of rabbits. We also have f2 equals 1 because the pair does not breed during the first month. And so to find the number of pairs in the island after n butts, add the number on the island after the previous month, that is f sub n minus 1, and the number of newborn pairs, which is equal to f sub n minus 2, because each newborn pair comes from a pair of at least 2 months old. Okay, there's more there that you can review, and you can also see Rosen. Okay, let's talk about the Tower of Hanoi. In the late 19th century, there was a French mathematician, Lucas, who invented a puzzle consisting of 3 pegs on a board with discs of different size. Initially, all the discs are on one of the pegs in order of size, with the largest at the bottom. We have some rules and we have some goals. We want to get all of them from the first peg to the third peg, and you are allowed to move the disc one at a time from one peg to another, as long as the larger disc is never placed on a smaller. So this is the initial peg, and you're trying to get the move over to there. I'm not going to go through this solution, but if you want, you can just pause the video and go over this in detail. But this just illustrates another example, not just the rabbit population problem, where we can be using some of the concepts that we're discussing in this portion of the lecture. And then it continues on into this next chart. And there's also another one that's related to this Tower of Hanoi, where they had 4 pegs. And so this was proposed back in 1907. And you can see some of the exercises in Rosen for this part of the textbook to get some more context for that. Okay, that's a second illustration. Here's the third. And so now we can be thinking about counting bit strings. And as I've done before, I'll just go over the example and briefly outline some of the highlights from the solution. So we want to find a recurrence relation and give the initial conditions for the number of bit strings of length n without 2 consecutive zeros. How many such bit strings are there of length 5? So thus we've got this all laid out that we need. So A sub n denotes the number of bits of string of length n without 2 consecutive zeros. To obtain a recurrence relation for A sub n, note that the number of bit strings of length n that do not have 2 consecutive zeros is the number of bit strings ending with a 0 plus a number of such bits ending with a 1. And so you can see this graphic over here that I put in the corner to help us to be thinking about how we would go about doing this. And so the relationship between the current and the last 2 generations is laid here. This is for n greater than or equal to 3. So we're seeing some similarities between these 3 problems. So here are the initial conditions. And to obtain need to find, we use a recurrence relationship 3 times to find that. And so you can be getting into walking through the detail here, and I will refer you to Rosen to be thinking about. So here is just another example of these types of sequences where they're dependent on multiple predecessors. Okay, what about counting the ways to parenthesize a product? So find a recurrence relationship for C sub n, the number of ways to parenthesize the product of n plus 1 numbers, A0 all the way up to X0 all the way to Xn, to specify the order of multiplications. And so thus we see some complicated ways that we can be laying this all out. Note that, and then in terms of the solution, note that however parentheses are inserted in this sequence with operators remain outside all parentheses. The final operator appears between 2 of the n plus 1 numbers, say x sub k plus x sub k plus 1. Since there are c sub k ways to insert parentheses in the product, and k sub n minus k minus 1, ways to insert the parentheses in the products, then we can get this kind of relationship. The initial conditions can be set up where c sub 0 is equal to 1 and c sub 1 equals to 1. And so the sequence C sub n is a sequence of Catalan numbers. This recurrence relationship can be solved using the method of generating functions. And this is later in this lecture when we get a chance to be thinking about generating functions. Okay, so talking about some things that are Fibonacci type of sequences, we got a chance to go through that. Now let's look at resolving linear recursive relationships. So a wide variety of recurrence relations occur in models. Some of these recurrence relations can be solved using iteration, or some others via ad hoc techniques. However, one important case of recurrence relations can be explicitly solved in a systematic way. These are recurrence relations that express the terms of a sequence as a linear combination of previous terms. So we'll talk about linear homogeneous recurrence relations. We'll talk about solving linear homogeneous recurrence relations with constant coefficients and solving linear non-homogeneous recurrence relations with constant coefficients. Okay, for linear homogeneous recurrence relations, we have a definition here. A linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relationship of the form that's shown here, where k sub 1, c sub 1, c sub 2, all the way to c sub k are real numbers, and k sub 0 is unequal to, c sub k is unequal to 0. So I'll let you follow through the rest of the things that are listed on this chart, but I'll keep moving along. And so here are examples of linear homogeneous recurrence relationships. So a linear homogeneous recurrence relation of degree 1. So it's one, it's only related to the previous term. Linear homogeneous recurrence relationship of degree 2. So it's related to 2 previous terms. We have a nonlinear homogeneous recurrence relation. So we have a sub n minus 1 plus a squared a sub n minus n minus 2. Non-homogeneous, and so we have a factor of 2 that's added into it. And then finally, instead of having just a fixed value, we have a variable, and so the coefficients are not constant. So these are all kind of examples that get into what we're trying to explore in this part of this lecture. So how do we go about solving linear homogeneous recurrence relations? The basic approach is to look for a solution to the form a sub n equals r to the n, where r is constant. Note that a sub n equals r to the n is a solution to the recurrence relationship that's shown here. We can do some algebraic manipulation that yields a characteristic equation. And so the sequence a sub n with a sub r equals r to the n is a solution if and only if if r is a solution to the characteristic equation. And so this is something that we're going to be looking at, coming up with solutions for this characteristic equation. The solution to the characteristic equations are called the characteristic roots of the recurrence relation. The roots are used to give an explicit formula for all solutions of the recurrence relation. So here is a theorem. Let C1 and C2 be real numbers. Suppose that R squared minus C1R minus C2 equals to 0 has 2 distinct roots, R1 and R2. Then the sequence A sub n is a solution to the recurrence relationship A sub n is equal to C1 A sub n minus 1 plus C2 A sub n minus 2. If and only if A sub n is equal to alpha R1 to the n plus alpha 2 R2 to the n. for n equals 0, 1, 2, dot, 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 where alpha 1 and alpha 2 are constants. So how will we go about using this? What is the solution to the recurrence relationship that we list here? And so you can see this, what we have here, the characteristic equation is r squared minus r minus 2 equals to 0. We can calculate what the roots are. And so therefore, a sub n is the solution to the recurrence relationship if and only if a sub n is equal to alpha 1, 2 to the n plus alpha 2 minus 1 to the power n for some constant alpha 1 and alpha 2. So we can find the constants alpha 1 and alpha 2, and we can solve the equation, and hence we can get the solution here in a closed form as we have here in the last line. So we can find the explicit formula for a Fibonacci numbers. We talked about this in the last section. So we can use theorem 1 to find an explicit formula for the Fibonacci numbers. The sequence of Fibonacci numbers satisfies the recurrence relationship f sub n is equal to f sub n minus 1 plus f sub n minus 2 with the initial conditions f sub 0 equals to 0 and f sub 1 equals to 1. So we can figure out what the roots of the characteristic equation r squared minus r minus 1 equals to 0. And here are those values. So we get a chance to be doing a little bit of algebra here. And then we don't show all the details. And then finally, we can come up with the Fibonacci numbers. And so this is what we calculate here as a result of walking through this mathematics. And you can go ahead and just pause the video if you want to be thinking about that in more detail. So for another type of problem we can encounter is what is the solution when there is a repeated root? Let C1 and C2 be the numbers with C2 unequal to 0. Suppose that r squared minus C1r minus C2 equals to 0 only has one repeated root r0, then the sequence a sub n is a solution to the recurrence relationship a sub n equals to c1 an minus 1 plus c2 an minus 2 if and only if we have this relationship a sub n equals to alpha r sub 0 n plus alpha 2 n sub r0 to the n for n equals 0, 1, 2, dot, 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 where alpha 1 and alpha 2 are constants. So here's an example. So what is the solution to the recurrence relationship that's shown here? So we can come up with the characteristic equation. We can solve for the constants, plug that in, and then we can get this final value here. Similar in methodology as what we talked about in a couple of slides before this. So how do we go about solving linear homogeneous recurrence relationships of arbitrary degree? So the theorem can be used to solve linear homogeneous recurrence relationship with constant coefficients of any degree when the characteristic equation has distinct roots. So here is another theorem that we can see that's going to be helpful for us to be doing this. I'm not going to go through this in detail. And here is the general case with repeated roots allowed. So here is another theorem that gives us some more interesting details of how we can go about doing that. And I'll refer you to Rosen for some of the details there. For linear non-homogeneous recurrence relationship with constant coefficients, a linear non-homogeneous recurrence relation with constant coefficients is a recurrence relationship of the form that's listed here, where C1, C2 up to CK are real numbers and f sub n is a function not identically zeroed depending only on n. We have the recurrence relationship that is listed here, and it is called the associated homogeneous recurrence relation. Um, the following are the linear non-homogeneous recurrence relations with constant coefficients. And you can see those are laid out here. With the following are the associated linear homogeneous recurrence relation respectively. So this is more details. I'll refer you to Rosen to be thinking about this in more detail. Then we can have the tools to go about solving linear non-homogeneous recurrence relations with constant coefficients. And so here is a theorem that's going to help us accomplish that. And here is an example, and I won't go through this either, but just skip over to the next session. So I'm just going to go back to a previous chart just for a minute. And so basically, we're getting a chance to be walking through some of these kind of relations and start to lay them out with some examples. And I'll just refer you to Rosen to be thinking about that in more detail. So some of this gets a little theoretical, and I'm trying to bound some of the complexity that we talk about in these survey lectures. Okay, let's get into divide and conquer algorithms and recurrence relations. That will be what we have here. And now we're going to be getting into how we can assess a couple different types of algorithms of things that we would be interested in if we're trying to explore this from a computer science point of view. Many recursive algorithms take a problem with a given input and divide it into one or more smaller problems. The reduction is successfully applied until the solution of the smaller problems can be found quickly. For example, we can perform a binary search by reducing the search for an element in a list to the search for this element in a list half as long. We successfully apply this reduction until one element is left. When we sort a list of integers using the merge sort, we split the list into two halves of equal size and sort each half separately. We then merge the two sorted halves. Another example of this type of recursive relation is a procedure for multiplying integers that reduce the problem of the multiplication of two integers to three multiplications of pairs of integers with a half as many bits. This reduction is successfully applied until integers with one bit are obtained. These procedures follow an important algorithmic paradigm known as divide and conquer and are called divide and conquer algorithms because they divide a problem into one or more instances of the same problem of smaller size, and they conquer the problem by using the solution of the smaller problems to find a solution of the original problem, perhaps with some additional work. So in this section, we will show how recurrence relations can be used to analyze the computational complexity of divide and conquer algorithms. We will use these recurrence relations to estimate the number of operations used by many different divide and conquer algorithms, including several that we have introduced in this section. So a divide and conquer algorithm works by first dividing a problem into one or more instances of the same problem of smaller size and then conquering the problem using the solution to the smaller problem to find a solution of the original problem. So we have been exposed to these, a binary search and a merge sort. So the binary search we covered in chapter 3 and 5, and the merge sort, we got a chance to talk about that in chapter 5. So now we're going to have some more things we can be thinking about that with the information we have in this chapter. Suppose that a recursive algorithm divides a problem of size n into a subproblems. Assume that each subproblem is the size of n divided by b. Suppose G of n extra operations are needed in the conquer step. The Fn expresses, the Fn represents the number of operations to solve a problem of size n satisfies the following recurrence relation. F of n is equal to AF of of n divided by b plus g of n. This is called a divide and conquer recurrence relation. So here's an example for a binary search. Binary searches reduce the search from an element in a sequence of size n to a search in a sequence of n divided by 2. The two comparisons are needed to implement this reduction, one to decide whether to search the upper or lower half, and the other determine if the sequence has elements. Hence, if f of n is the number of comparisons required to search an element in a sequence of size n, then f of n is equal to f of n divided by 2 plus 2 when n is even. Okay, for a merge sort, the merge sort algorithm splits a list of n. That is assuming that n is even. You can't have an odd, and then you have to figure if you're where you're gonna put that odd element in the lower or upper half. But items can be sorted into two lists with n divided by 2 items. It uses fewer than n comparisons to merge the two sorted lists. Hence, the number of comparisons required to sort a sequence of size n is no more than m of n, where m of n is equal to 2m n divided by 2 plus n. We have another example of fast multiplication of integers, an algorithm for the fast multiplication of 2 n bit integers, and assuming that n is even, first splits each of the 2 n bit integers into 2 blocks each of n bits. So I'm not going to go through this in detail, but you can walk through this in Rosen or just pause the video and see here. But what we get to is we have f of n is the total number of operations needed to multiply the 2 n-bit integers, and it can be found here, where c of n represents the total number of bit operations, the additions, subtractions, the shifts that are a constant multiple of n-bit operations. So those are a couple examples where we can be using this. So how do we go about estimating the size of divide and conquer functions? So now we can be getting into the complexity, big O notation complexity. Let f be an increasing function that satisfies the recurrence relationship that's shown here. Whenever n is divisible by b, where a is greater than or equal to 1, and b is an integer greater than 1, and c is a positive real number, we get this relation. So we can see that we have two different cases of big O notation of complexity. So further, when n is equal to b to the k power and a is unequal to 0, when k is a positive integer, then we have this kind of a relationship that's laid out. Okay, complexity of binary search. The binary search example giving a big O estimate for the number of comparisons used by binary search. Since the number of comparisons used by binary search is f of n is equal to f of n divided by 2 plus 2, where n is even, then using a theorem that we've already had talked about in this chapter, it follows that f of n is, in terms of complexity, big O notation of log n. So that's a useful value that we can be now taking a binary search and compare it with other types of search algorithms. So here is another theorem. Let f be an increasing function that satisfies this type of recurrence relation when n equals to b to the k, where k is a positive integer greater than 1, and c and d are real numbers with c positive and d non-negative. And then we get this three possible relations depending if it's one or three of these cases. Great A is greater than B to the D if it's equal to, or if A is greater than B sub n. So less than, equals, or greater. Okay, in terms of the complexity of the merge sort, and so We want a big O notation of its comparisons used by the merge sort. Since the number of comparisons used by the merge sort to sort a list of n elements is less than m of n, where m of n is equal to 2m n divided by 2 plus n, by the master theorem that we just showed on the last slide, we have that the big O notation is n log n. So merge sort, big O notation n log n. For binary search, it's big O notation log n. And so now we're starting to get a collection of things that we can be using to help us out. Okay, for the fast integer multiplication, we see that it has a big O notation of n squared. I'm not going to walk through this details, but now with this advanced counting techniques and the material that we're covering in this chapter, we can actually quantify 3 different types of algorithms that we will find useful, and we've done that, and now we can be using that. Okay, well, let's move on to generating functions. So here's the material that we'll cover here. These last 2 parts are in Rosen, but we won't cover them in the lecture. Generating functions are used to represent sequences efficiently by coding the terms of a sequence as coefficients of powers of a variable x in a formal power series. So power series is what we're going to get a chance to figure out how to deal with. Generating functions can be used to solve many types of counting problems, such as the number of ways to select or distribute objects of different kinds, subject to a variety of constraints, and the number of ways to make change for a dollar using coins of different denominations. Generating functions can be used to solve recurrence relations by translating a recurrence relationship from the terms of a sequence into the equations involving a generating function. This equation can then be solved to find a closed form for the generating function. From this closed form, the coefficients of the power series for the generating function can be found solving the original recurrence relation. Generating functions can also be used to prove combinatorial identities by taking advantage of relatively simple relations between functions that can be translated into identities involving the terms of sequences. Generating functions are a helpful tool for studying many properties of sequences besides those described in this section, such as their use for establishing asymptotic formula for the terms of a sequence. So generating functions, counting problems in generating functions, useful generating functions, these are the things that we're going to be focusing on. So we can see that this is the general characteristic of what a generating function would be looking like. And so we have this kind of relationship. And so here are examples that we can be thinking about. So you can be referring to that as you would like, or I'd refer you to Rosen. So generating functions for finite sequences of real numbers can be defined by extending a finite sequence A0, A1, dot, 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 to A sub n into an infinite sequence by setting A sub n plus 1 equals to 0, A sub n plus 2 equal to 0, and so on. The generating function g of x of the infinite sequence A sub n is a polynomial of degree n because no terms of the form A sub j x to the jth power with j greater than n occurs. That is, we have this kind of a relationship. So how do we go about generating functions for finite sequences? And so here we see a sequence where it's all ones. And so this is what we end up coming up with to solve this type of relationship. And so that's just one example. I know this is going to be really hard to read, but this is table 1 in this chapter, and I would refer you to Rosen to go ahead and look up this in more detail to get this idea of what these generating functions would look like. And we just see one example for this type of a sequence that's we have just talked about. And so we can be thinking about it a couple different ways. And so we could, and thus we see these different ways that we could be listing it there. And then we have the generating function. And so that's just a nice summary. So in terms of counting problems and generating functions, find the number of solutions of E1 plus E2 plus E3 equals to 17, where E1, E2, and E3 are non-negative integers with 2 less than or equal to E1 less than 5, 3 less than or equal to E2 is less than 6, 4 less than or equal to E3 less than or equal to 7. And so here is a summary of what we have there that you can look over. So the number of solutions to this coefficient is x to the 17, and the expansion of this follows because a term equal to is obtained in the product by picking a term in the first, some e to the E1, a term in the second, e to the E2, and a term in the third, e to the E3, where E1 plus E2 plus E3 is equal to 17. There are 3 solutions since the coefficient e to the 17th is the product of 3. Here is another example. Use generating functions to find the number of k combinations of set with n elements, that is C of nk. And so each of the n elements in the set contributes a term 1 plus x to the generating function that we have here. Hence, f of x is equal to 1 plus x to the nth power, where f of x is the generating function for ak, where ak represents a number of k combinations of the set with k elements. We can be using the binomial theorem to come up with the final result that we have listed there. Okay, now let's talk about inclusion and exclusion, and we'll be using some graphical ways of thinking about this that may give us some interesting insight. So a discrete mathematics class contains 30 women and 50 sophomores. How many students in the class are either women or sophomores? So this is the kind of question that we can address with the tools we're going to learn here. So this question cannot be answered unless more information is providing. Adding the number of women in the class and the number of sophomores probably does not give the correct answer because women sophomores are counted twice. This observation shows that the number of students in the class that are either sophomores or women is the sum of the number of the women and the number of the sophomores in the class minus the number of the women sophomores. A technique for solving such counting problems was introduced in section 6.1, and in this section we will generalize the ideas introduced in that section to solve problems that require us to count the number of elements in the union of more than 2 sets. So we have this kind of relationship. You can be thinking of sophomores and women, and so we don't want to overcount. So we have this last term to help us to make sure that we do this properly. So then, thus, if we use a Venn diagram, and we'll be using this several times in this section, it's going to be helpful for us to be figuring out these results. So basically, we can be using these values, and we've got it figured out here for us. And so thus we can come to a solution that we don't overcount and get the right number. So here is another example. So this is, say, with 2. Now if we're trying to engage with 3 values, it gets more complicated. So the first diagram shows the count of elements by the formula number of the elements in A plus a number of elements in B plus a number of elements in C. There is number 1 in exactly one of these three sets, number 2 in the intersection of any of the two sets, and number 3 in the intersection of all three sets. So we can see that for the first one. For the second diagram, it shows a count of elements by the formula number of elements in A plus a number of elements in B plus a number of elements in C minus the number of elements in the intersection of A and B minus the number of elements in the intersection of A and C minus the number of elements in the intersection of B and C. There is number 1 in exactly one of the three sets in the intersection of any of the two of the sets, and number 0 in the intersection of all three sets. Finally, the third diagram shows count by elements by the formula number of elements in A plus a number of elements in B plus a number of elements in C minus the number of elements in the intersection of A and B minus the number of elements in the intersection of A and C minus the number of elements in the intersection of B and C plus the number of elements in the intersection of A, B, and C. There is number 1 in exactly one of the three sets and in all of the intersections. And so we can still graphically conceive this with three finite sets, and hopefully that explanation gives you a little better sense of what we can do. So here is another example for three sets. A total number of 1232 students has taken a course in Spanish, 879 have taken a course in French, 114 have taken a course in Russian. Further, 103 have taken courses in both Spanish and French, 23 have taken courses in both Spanish and Russian, and 14 have taken course in both French and Russian. If 2092 students have taken a course in at least one of Spanish, French, and Russian, how many students have taken a course in all three languages? Well, the ultimate value is 7, and I just refer you to this figure here that helps us to come up with that final value here, and we got a chance to be walking through that in this last slide. So here is the principle of inclusion exclusion. The principle of inclusion exclusion, let A1, A2, A and be finite sets. Then we have this type of a relationship that we can be utilizing. So I'm not going to walk through the proof, but this is something that Rosen has, and you can take your time to go through that. So that's about the amount of time I want to be spending on that section. I'm going to go ahead and then move on to the applications of inclusion and exclusion, and we'll finish up that section that way. So many counting problems can be solved using the principle of inclusion and exclusion. For example, we can use the principle to find a number of primes less than a positive integer. Many problems can be solved by counting the number of onto functions from one finite set to another. The exclusion principle can be used to find the number of such functions. The well-known hat check problem can be solved using the principle of inclusion exclusion. The problem asks for the probability that no person is given the correct hat back by a hat check person who gives the hat back randomly. And we'll see that in a handful of charts here. So here's an example. How many onto functions are there from a set with 6 elements to a set with 3 elements? So I'm not going to walk through this solution, but the ultimate value for this is 540. And you can feel free to pause the video and walk through that in more detail. Here's a theorem. Let m and n be positive integers with m greater than or equal to n. Then there are we have this format that we have, onto functions from a set with m elements to a set of n elements. And the proof is in Rosen, at least it's suggesting that you can be walking through that. You can see exercise 27. Derangement. Derangement is a permutation of objects that leaves no object in its original position. So we have this value is a derangement of 1, 2, 3, 4, 5 because no number is left in the original position. But 2, 1, 5, 4, 3 is not a derangement of 1, 2, 3, 4, 5 because 4 stays in the same position. So the number of derangements of a set with n elements is what we have laid out here. And you can see the text for the solution. And this hat check problem uses this value here. And so it gives everybody the wrong hat is what ends up happening. And it can't be shown that the probability of a derangement approaches 1 over E as n grows without bound. And we can see this relationship. And so I think we haven't talked about it, but this is one of those natural constants that we utilize in math and physics and engineering. So just wanted to point out what that is. Okay, we've covered a lot of information. I've tried to keep it at a top level, but it's still, there is some complicated things that I didn't get a chance to go into a lot of details. So thank you very much. Have a good day.